This video is a walkthrough for the software implementation of a 16-bit 128 tap FIR filter. Once you open Quartus, you make a new project. I have a folder which will be the working directory for my project. This is the name for my project, and I have to change the top level design entity name for the project, as the system which I will generate in Qsys will have the same entity name as the top level design entity for Quartus. Hit next. In the device and settings, we have a DE1 board with a pin count of 484 and a speed grade of 7. In the EDA tool settings, we use Model Sim for simulation, and the hardware language used is Verilog HDL. After creating the system, we go to the Qsys tool. Qsys will automatically create an interconnect logic from the high level connectivity you specify it with. Here you use the NIOS 2 processor. We opt for the economical version since it's free and no license is required. It supports up to 256 custom instructions. It has a JTAG debug module. The on-chip memory, we make sure that we have 8192 MB of RAM to be on the safer side. After this, we have the JTAG interface, which is used to communicate with the system. We also have the performance counter, which is needed to calculate the components performance, which we'll later use to compare it with the hardware implementation of our project. We add clock to all the system components as well as the reset component. All the blocks receive the data master for its communication. We have to make sure that the interrupt pins are connected as well. After this, we assign the base address to all the components. As you can see, we have some errors. These errors are because the base addresses have not yet been defined. Assign the interrupt and the reset vector to the on-chip memory, which will allow us to generate the system. This intel will generate Verilog files. After this, you can save the system. When you save the system, the name should be exactly as the top level entity in Quartus, as the top level module remains the same in both Quartus and Qsys. After generation, we add the QIP file in the project. You have an option of importing all the Verilog files which Qsys has created. The next step is using the assignment editor tool, which will allow you to assign the pin connections for the clock. Since all the components are built in, we just need to assign the pins to the clock. Location of the clock is pin underscore L1, and it uses a 3.3 VLVTT standard. Save and compile your design. While the system is compiling your design, we can go to NIOS 2 Eclipse. A thing to remember here is to make sure the work directory for Eclipse remains the same. You can delete the previously generated files. This is because I already had run the design earlier. Creating a new project in NIOS 2. Name the project accordingly. Make sure the directory remains the same. Do not choose the default location if it appears that the path address is invalid. After finishing, we use a template to test the system. NIOS 2 provides us with a hello world C file, which basically tells us whether or not the system is communicating or performing perfectly. We replace the hello C code with the code which we have for our 128 tap FIR filter. Before doing that, we add the output file, the SOF file. Which will allow us to run the code on NIOS 2. Right click and build your project in NIOS 2 Eclipse. This is the last step, or rather the second last step of our software implementation of the project. Once the project is built, all you have to do is run it on as a NIOS 2 hardware. As you can see, the results, the number of cycles which software takes is far more than hardware, which is 175,489 cycles. The output is the same, but the number of cycles is way more than the number of cycles we have in hardware.